Okay, now it's not always going to be this easy. Just be real careful on this. What if I take the limit as x approaches 0 from the positive side of something like this? How about x ln x? Okay, so when I plug this thing in, I get 0 times, oh crap, negative infinity. Well, this is kind of one of those where who wins the battle? I mean, I don't know. Do I get to 0 fastest? And then I don't care how big of a number you stick in, because when I multiply by 0, it goes to 0. Or does this thing get to negative infinity so fast that 0 doesn't have a chance to catch up? Because remember, we're taking limits, right? Or, strangely enough, does it meet somewhere in between? Well, let's check it out. This clearly is not a L'Hopital's indeterminate form. That's either going to be 0 over 0 or infinity over infinity, right? So what I have to do is algebra. And it's not even that big of a deal. Watch what I'm going to... Well, I don't know where that fraction bar came from. Sorry, you guys. Getting a little crazy. I just had lunch, so I had some Coca-Cola with lunch. I'm a little spastic. So I'm simply going to use a fancy little trick. But it's not so fancy. I mean, we really technically learned it in 3rd grade. Do you agree that x can be written as 1 over x, right? 1 over x equals x, right? If I take the reciprocal of a reciprocal, I get the thing back. Now look at what happens. I know that the limit as x approaches 0 from the positive side of the natural log of x is equal to negative infinity. I know that the limit as x approaches 0 from the positive side of 1 over x is positive infinity. Dun, da, da, da. We have L'Hopital's. So go nice and slow. We're simply going to take the derivative. I love L'Hopital's. It's so much fun. I'm going to take the derivative of the natural log of x, which is 1 over x. I'm going to take the derivative of 1 over x. Hopefully this thing's on the hard drive. I know it gets hard when you leave these things and then come back to them, but it's a piece of cake. It's negative 1 over x squared, just because x is, or 1 over x is x to the negative 1. Now I'm going to do a little bit of algebra, because if I just start throwing zeros in again, I'm going to get infinities over infinities. But hopefully you can see that this thing's just begging to have some algebra done to it. Now notice I did not put a L'Hopital's H in here. I'm not doing L'Hopital's, I'm doing algebra. So I'm just sticking an equal sign. It just says, hey, I'm doing some algebra here. There's a difference between doing algebra and doing L'Hopital's, and you need to make sure that you note that difference. All right, so let's see. If I multiply x squared on top, what do I get? I get negative x squared over x, which is affectionately known as the limit as x approaches 0 from the positive side of negative x, which, guess what that is? It's 0. It looks as though this guy gets to 0 before this guy can get to infinity. Now, be careful. Another thing that I want to make sure that you guys do is don't drop this limit. All right? We're taking limits throughout this whole thing. If this limit starts going away, and you'll be, Ripley, I would never do that. Oh, yes, you will. You will forget to include the limit, and all of a sudden I've just got these algebraic jellyfish cruising along. Okay? Look, negative x squared over x is not equal to the limit as x approaches 0 from the positive side of negative x squared over x. You need to make sure that you talk about the limit. Okay? Sound good? All right. Try this one on your own. I'll give you just a little break to get something done. How about this? How about the limit as x approaches, let's go 0, of tan x minus x over x cubed. All right? So just pause the video and try it. All right? Just try it from start to finish. Pause the video. I'll give you a second, and then I'll pick it up. Okay? Go ahead. All right, hopefully you tried that out. So the first thing I'm hoping that you did is you plugged in 0, and you got 0 minus 0, it's actually known as 0, over 0. All right, so by L'Hopital's, I know that this is equal to the limit. Make sure that you're doing that, right? What's the derivative of tan again? Oh, that's right, it's secant squared x minus 1 over 3x squared. All right, what's this thing equal? Well, wait a sec. Secant is 1 on cos, and the cosine of 0 is 1. No, crud. Well, let's see. Cosine is 1. 1 squared is 1. Oh, man, I end up with 0 over 0 again. Well, let's just keep on doing L'Hopital, shall we? But wait a sec. Is there anything that we can do that's clever? All right? Is there anything that we can do that might be just a little bit clever? I don't see it. The nice thing is that when I look at this, There, if I take enough derivatives of 3x squared, eventually that thing's going to go to a number other than 0, right? So that tells me at least, I mean, it may be awful. I may have to take a whole bunch of derivatives. But if I take enough, I will get a value other than 0 in the denominator, right before. In other words, I'll get a constant. So let's look. This is equal to the limit, whoops, as x goes to 0, of, ooh, this is blah squared. So this is going to be 2 secant x, right, blah squared to the first times the derivative of secant, which is secant x tan x. Hey, that's weird. Look at what I'm getting back. And then this thing just goes to 0, so minus 0 all over 6x. Okay, so let's have a peekaboo. Now, well, the tangent of 0 is 0. The secant of 0 is 1, right? So this still ends up being, well, crud, 0 minus 0 is 0 over 0. However, you know what? I probably should take a minute just so I don't do anything stupid. But no, we're not going to do L'Hopital's. We're going to do a little bit of algebra first. Just to clean it up, it'll be an easier derivative to take. So this is equal, notice, no L'Hopital's, the limit as x approaches 0 of 2 secant squared x tan x over 6x. Now, you may be looking at this thing right now and just going, oh man, Ripley, this is nasty. Now, wait a sec, though. Is there anything clever that we can do? I mean, if I look at this and I'm like, I don't want to take the derivative of this. If I do L'Hopital's, I'm going to be taking the derivative of this god-awful, nasty monstrosity here. So don't abandon all of the information that you already have. Don't abandon your algebra. Don't abandon your limit rules. I see tangent x over x sitting right there. And I remember back from limits, I remember that the limit as x approaches 0 of tan x over x. Remember, if I take the limit as x approaches 0 of tan x over x, isn't this equal to the limit as x approaches 0 of sine x over x times 1 over cos x, right? Remember that? And we know what this limit is. We just proved it. It's 1. I know what this limit, remember, the limit of a product is the product of the limits. And this is 1 as well, because cosine of 0 is 1. Ooh, sweet. So I can rewrite this as the limit. Notice no L'Hopital's. I'm not doing anything that I don't have to. Let's say I've got 2 secant squared x over 6, which is really just secant squared x over 3 times the limit as x approaches 0 of tan x over x. Now let's see what happens. Secant of 0 is 1, because the cosine of 0 is 1, and secant's just 1 over cos, right? So this first term just turns into a 1/3. The second term we just proved turns into a 1, and guess what? It equals 1/3. Isn't that awesome? That's a fun one. All right, so the moral of the story is don't abandon your algebra. Always be thinking of clever, really clever ways. Students that were good at trig identities are good at problems like this, because they're always kind of looking for that. Remember trig identities when you had to figure out the little shoehorn and how to change something around? It's the same sort of deal. These can be a little bit nasty. Excuse me. Okay, let's do something interesting. I'm going to pull a problem directly out of the text. This is a good problem. Your author really does write nice problems. So from time to time, you can also write some crazy problems, but it is what it is. I'm going to do 1 plus sine of 4x, and I'm going to raise this to the cotan x. Okay? Now, it's a good problem, and I want you to be able to follow along, because these are the types of problems that are going to give you fits if you're not careful, because you will see these again, I promise you. Now, first things first, just like we always do. If I plug 0 in, I get 1 plus 0, which is 1, right? And then if I plug 0 into cotan from the positive side, wait a sec, cotan, what's that look like? Cotan, oh, right, cotan looks like this. Crap, it's to the infinity. Now notice, for L'Hopital's to be able to work, I either need this, or I need this, or I'm screwed. All right, so what does that tell me? It says do some algebra. Algebra that you're going to have to do is going to be a little bit tricky. I'm going to take you on the long road on this one, but bear with me for a sec. I'm going to introduce an e to the ln of something. And the reason why is if I've got to make it look like one of these two, and I've got it raised as an exponent, I have to get rid of this exponent term. And the best trick that I have for that is taking the natural log of something. Remember back in Algebra 2 when we had to solve for variables that were exponents? That's what I'm going to do. Now notice e to the natural log of anything is that anything, and it gets me right back where I need to. Now there's another trick here. Do you remember from your laws of limits, if I take a continuous function e to the x and I take the limit of e to the something, this is exactly the same thing as e to the limit as x approaches 0 from the positive side of the natural log of 1 plus sine of 4x raised to the cotangent of x. Now from this point hence, I'm going to use an implies arrow here instead of an equal sign because they're not going to be equal. From this point hence, I am only going to concern myself with this exponent of e, but we'll come back to it. We're going to need that here in a sec. All right, so let's look at this. Remember why I put the natural log here in the first place? So I could bring the cotangent down as a coefficient rather than dealing with it as an exponent. So let's see what happens. I'm going to get the limit as x approaches 0 from the positive side of the cotangent of x times the natural log of 1 plus sine of 4x. Now, let's just watch what happens here. Okay? So take a gander. Maybe this will help. I'm still going to get infinity times, let's see, the natural log of 1, which is 0. Oh, crud, that's another weird indeterminate form. I don't know who wins, the 0 or the infinity. So I'm going to do a little algebra here. Notice I haven't even used L'Hopital's yet. Why? Because it's not in one of these two forms. Isn't cotan x just begging to have something happen to it? Remember from your trig? Isn't cotan x just 1 over tan x? So can't I rewrite this as the natural log of 1 plus sine of 4x over tan x, because 1 over tan x is cotan x. Now let's see what happens. I plug 0 in. Sine of 0 is 0. 1 plus 0 is 1. The natural log of 1 is 0. Sweet. Tangent of 0. Oh, look at that. So now we get to use L'Hopital's. This is equal to the limit as x approaches 0 from the positive. Just take the derivative. Now, careful. I say that sort of glibly, but it's a hard derivative to take. So let's go slowly. It's the natural log of blah, which is just 1 over blah, right? 1 plus 10 or x, but times d blah, right? And the derivative of the sine of 4x is the cosine of 4x times 4. I'm going to stick that 4 out here as a coefficient. So I actually had to use the chain rule twice there, didn't I? The natural log of blah, but the blah also had a crazy little composition in it. So we got to be real careful of that. And then divide it by secant squared x. Hopefully you've got that one on the hard drive. Now let's look close. If I plug 0 in, you know what? I'm going to change colors just so I can see what's going on here. When I plug 0 into this term, I get 1, right? Because sine of 0 is 0. 1 plus 0 is 1. 1 over 1 is 1. So this equals 1 times, when I plug 0 into this term, I get 0. Cosine of 0 is 1. Oh, look at that. I got 4. Sweet. We finally got a number other than 0 or infinity. And then secant squared, well, secant's just 1 over cos. Cosine of 0 is 1. 1 over 1 is 1. 1 squared is 1. Guess what? Now, this is typically when students run around with their hands in the air and say, hallelujah, I'm done, Ribley. I'm done. Give me another problem. Yeah. Rarely. However, we got to remember, we pulled this limit from atop the e. This number right here is this limit right here. However, remember, we were just dealing with the limit as an exponent of e. So doesn't this imply that the limit as x approaches 0 from the positive side of 1 plus sine of 4x raised to the cotan of x, isn't that equal to, remember, if this equals this, and we know that this equals this, and this limit right here equals 4, and this is just e to the 4th. Ta-da! Smiley face. And that's it. We'll do a lot more like that, you guys. It's a fun one. It's a trick. You'll see it again, I promise. Wink, wink, nudge, nudge. You might even see it on a test or a quiz. So, hope you enjoyed. We'll see you tomorrow. Excuse me. We'll do a whole bunch of these. All right. Have a really good day. Bye.